Hello, and welcome to this module on Zscaler Connectivity Services. I'm glad you're here because what we're going to cover today is truly the backbone of how Zscaler works. This isn't just theory. Everything in this session is something you'll use when designing, deploying, and troubleshooting real Zscaler environments. In this module, we'll be covering 4 big areas. First, we'll look at how connectivity works at a conceptual level. What it really means to replace traditional VPN-style networking with something called identity-centric routing. Second, we'll go through all 3 forwarding methods: zTunnel 2.0 for user devices, GRE and IPsec tunnels for sites and data centers, and pack file forwarding as a browser-based option. Third, we'll explore the core components: client connector, cloud connectors, branch connectors, and understand exactly what each one does and when to use it. And fourth, we'll look at DNS and routing, which are 2 areas where a lot of real-world deployments go wrong, often silently. Everything here ties directly to ZTA exam objectives. So as we go through each slide, listen for the exam angle, because the patterns we're building here are exactly what those design and scenario questions test. Let's get started. Let me start with a question. How does traditional enterprise networking decide whether to trust someone? The answer is by their network location. If you're inside the office or connected through a VPN, you're trusted. The assumption is that the network itself is the security boundary. Get onto the network and you have access. That's the old model, and for a long time it worked, but it has some serious problems. When a device on the trusted network gets compromised through phishing or malware, the attacker can move freely to any other system on that flat network. There's no internal boundary stopping them. On top of that, the hub-and-spoke VPN model creates latency. A user in London might need to backhaul traffic through a corporate VPN gateway in New York just to reach a cloud application, adding hundreds of milliseconds of unnecessary delay. And as organizations grow and become more distributed, VPN becomes harder and harder to scale. Zscaler solves this differently. Instead of asking, "Is this device on the network?" it asks 3 questions for every single connection. Who are you? Meaning your authenticated identity. What device are you on? Meaning, does it meet our security requirements? And where are you trying to go? Meaning, is this something you're authorized to access? If all 3 check out, Zscaler creates a connection, not a network extension, a precise, short-lived connection from that specific authenticated user on that specific verified device to that specific resource. Nothing more. There are 3 ways traffic actually gets to Zscaler. The first is zTunnel 2.0, which is used by Zscaler Client Connector on user devices. It wraps all traffic, not just browser traffic, everything, into encrypted DTLS or TLS sessions that are cryptographically bound to the user's identity and device posture. The second is GRE and IPsec tunnels, which are used at fixed sites like branch offices and data centers. Instead of putting an agent on every device, you configure the branch router or firewall to send all traffic through a tunnel to Zscaler. GRE is lightweight and efficient for trusted networks. IPsec adds encryption for untrusted paths. The third method is pack file forwarding, which is a browser-only option. A small JavaScript file tells browsers whether to route requests directly or through a Zscaler proxy. It's a fallback when you can't or don't want to install an agent. All 3 methods lead to the same place, the Zscaler Service Edge, where ZIA and ZPA apply the full security policy. The forwarding method is separate from the enforcement. That separation is fundamental to how Zero Trust works, and it's something you'll see come up again and again. Think of the Zero Trust Exchange as a city. The service edges are the city's infrastructure. The policy engine, ZIA, ZPA, is the rule set, the laws of that city. And connectivity services? They're the roads and bridges that bring everyone into the city in the first place. Without them, nothing else works. Traffic never reaches the service edge, policies never get applied, and your security controls exist only on paper. More precisely, connectivity services form the fabric that ties every endpoint, every branch office, and every cloud workload to Zscaler's global enforcement points. And they do something really important. They translate legacy networking concepts, IP addresses, subnets, VLANs, into zero-trust concepts, user identity, device posture, application segments, session context. That translation is what makes consistent policy enforcement possible everywhere. There's also a third function that's easy to overlook: telemetry. Every connectivity component continuously exports data, latency measurements, packet loss rates, tunnel health metrics, and this feeds Zscaler's analytic systems. This is what powers ZDX, Zscaler Digital Experience, which lets you see where in the end-to-end path a user experience problem is occurring. Now let's look at the three core components. The first is Zscaler Client Connector, the software agent installed on user devices. It authenticates the user through your identity provider, evaluates device posture, checking things like OS version, disk encryption, and endpoint agent status, applies your forwarding policies, and sends designated traffic over zTunnel 2.0 to the near service edge. It's the right solution for any user who carries a device with them. The second component is cloud and branch connectors. Not everything can run Client Connector. Virtual machines, containers, branch firewalls, legacy systems, these need a different approach. Cloud connectors act as forwarding agents for cloud workloads, sitting in your cloud environment and steering traffic from VMs and containers in a Zscaler for inspection. Branch connectors do the same at the network layer for physical locations where traditional tunneling isn't available. The third component is GRE and IPsec tunnels. Not Zscaler software you install, but standard networking protocols you configure on your existing edge devices to create tunnels to Zscaler service edges. A single tunnel from a branch firewall can forward traffic from hundreds of users simultaneously. These three components are complementary, not alternatives. A real enterprise deployment uses all three: Client Connector for users, GRE or IPsec for sites, and cloud connectors for workloads, all feeding into the same enforcement plane and the same logging pipeline. One important warning here: using the wrong component for a use case doesn't just mean suboptimal performance. It means traffic bypasses Zscaler entirely. If you deploy site tunnels but skip Client Connector, remote workers have no protection when they leave the office. If you deploy Client Connector but forget about cloud workloads, all that server traffic goes to the internet uninspected. These gaps are common in real deployments, and the exam tests your ability to spot them. Connectivity services deliver two primary functions continuously for every user, every session, every day. The first is traffic steering and policy enforcement. The second is authentication and session persistence. Let's walk through both. Traffic steering begins at the source, at the endpoint or the branch location, before traffic ever reaches Zscaler. On a device running Client Connector, the software intercepts traffic at the operating system level. There's a network driver sitting between your applications and the physical network interface. Every packet any application sends is evaluated here first. Client Connector applies your forwarding policy. This traffic goes to ZA, that traffic goes to ZPA, this other traffic goes directly to the internet, and then routes accordingly over zTunnel 2.0. At a branch office with a GRE or IPsec tunnel, the branch firewall does the steering. The firewall has policy rules that say traffic from these subnets goes through the Zscaler tunnel. Traffic for internal destinations stays local. For pack file deployments, the browser evaluates the pack file logic for every request and decides direct or proxy. Once traffic arrives at the service edge, the full Zscaler policy stack kicks in. Authentication is verified. The service edge confirms the session belongs to a known, authenticated user. Device posture is checked. Is this device compliant with your requirements? Then URL control, cloud application control, cloud firewall, IPS, and DLP are all applied in sequence. Because identity and device context travel with the traffic through the tunnel, every policy decision can be user-specific and device-specific, no matter where in the world that user is sitting. The key architectural insight here is the decoupling of steering from enforcement. The device decides where to send traffic. The service edge decides what to do with it. This means you can change your security policies centrally, and they instantly apply to every user globally. The remote worker, the branch user, the office user, all at once, without touching any endpoint configuration. Now, for session persistence. This matters because modern users move between networks constantly. They start at home on Wi-Fi, switch to a mobile hotspot in the car, arrive at the office, and connect to corporate Wi-Fi. Each of those transitions means a new IP address, a new network path, potentially a different DNS server. Traditional networking struggles with this. Zscaler handles it gracefully. When Client Connector detects a network change, which it does by watching operating system events, it refreshes its forwarding profile and reestablishes the zTunnel 2.0 to the near service edge. This typically completes in just a few seconds. zTunnel 2.0 prefers DTLS, which is the UDP-based protocol, because it allows very fast session establishment. If the new network blocks UDP, which happens on hotel Wi-Fi and some corporate guest networks, the tunnel automatically falls back to TLS over TCP. The user doesn't do anything. It just works. On the ZPA side, there's another layer of resilience. App connectors are typically deployed in groups of 2 or more. If one app connector fails, ZPA automatically redirects the session through another healthy connector in the group. Users experience a very brief pause, and then their session continues. No administrator action required, no user action required. All 3 forwarding methods share one common concept: tunneling. Tunneling means you take your original packet and wrap it inside another packet with a new header. The wrapped packet travels to an intermediate destination, the Zscaler Service Edge, which unwraps it, inspects it, and forwards the original to its actual destination. Think of it like putting a letter inside an envelope. The envelope is addressed to the post office. The post office opens it, checks the contents, and then delivers the inner letter to its real recipient. What differs between the 3 methods is the encapsulation protocol, the level of encryption, and the use case each is designed for. zTunnel 2.0 is the gold standard for user devices. When Client Connector is installed, it intercepts traffic at the OS level, either at the IP routing layer for all traffic coverage or at the proxy layer for browser-focused deployments. It then encapsulates that traffic inside DTLS or TLS sessions directed to the nearest service edge. What makes zTunnel 2.0 special is that the tunnel session itself is authenticated. The session is cryptographically bound to the user's identity and device registration. So when a packet arrives at the service edge, the policy engine already knows. This is Sarah from the finance team. On a company-managed laptop, last posture check showed compliant. Session started at 9:15 this morning. Every packet carries all of that context implicitly. There is one absolutely critical fact about zTunnel 2.0 that you need to memorize. It is required to enable cloud firewall in ZIA. This is not a preference. It is an architectural requirement. Legacy tunnel modes are proxy-based, which means they only work for HTTP and HTTPS. zTunnel 2.0 encapsulates at the IP layer, which means it handles any protocol, any port, TCP, UDP, DNS, VoIP, everything. That full protocol coverage is what makes Layer 7 firewall inspection possible. No Ztunnel 2.0, no cloud firewall. Remember that for the exam. GRE tunnels use generic routing encapsulation. You configure them on your branch router or firewall, specifying your WAN interface as the source and a Zscaler Service Edge IP as the destination. The overhead is tiny, just 24 extra bytes per packet, making GRE very efficient for high-throughput connections. GRE is ideal for sites with trusted private network connectivity, like MPLS circuits, where encryption of the underlay isn't required. The main operational things to watch are MTU, because GRE headers reduce the effective payload size and cause fragmentation if you're not careful, and redundancy. Always run at least 2 GRE tunnels per location to different service edges. IPsec uses encapsulating security payload, ESP, which encrypts the packet and provides integrity protection. This is what you need when the underlying network path is untrusted. A standard internet connection, a third-party WAN, or any shared public infrastructure. IPsec is also the answer when your compliance framework mandates encryption for all WAN traffic. The trade-off is complexity. Phase 1 and Phase 2 negotiation, encryption algorithm selection, key lifetimes, rekey events. Modern firewalls and SD-WAN devices automate most of this, and Zscaler provides recommended configuration profiles for major vendors. Like GRE, always deploy at least 2 IPsec tunnels per location. A PAC file, proxy auto-configuration file, is a small piece of JavaScript that browsers download and run for every web request they make. The JavaScript contains a function that receives the destination URL and returns one of 2 things. Direct, meaning the browser connects straight to the destination, or proxy with a server address, meaning the browser routes the request through that proxy. In a Zscaler deployment, that proxy address is a Zscaler service edge. Here's how Zscaler makes this smart. When a browser fetches the Zscaler PAC file, Zscaler looks at the public IP of the request to determine the user's geographic location. Based on that, Zscaler generates a customized PAC file containing the IP addresses of the nearest service edges. A user in Singapore gets service edges near Singapore. A user in New York gets service edges on the East Coast. This geolocation happens automatically. No administrator configuration needed per user. Organizations can also upload custom PAC files with more granular logic. You can create rules based on specific URL patterns, specific domains, or destination IPs. For example, you might exclude internal IP ranges from being proxied, or you might bypass Zscaler for certain legacy applications that are known to break through proxy. PAC file forwarding is the right choice in a few specific situations. First, when you genuinely cannot install Client Connector, the device is managed by a third party, it runs an unsupported OS, or the organization is in an early pilot phase. Second, when you only need to protect browser-based HTTP and HTTPS traffic and non-browser application traffic is not in scope. Third, PAC files also exist inside Client Connector itself. When Client Connector operates in tunnel with local proxy mode, it uses PAC-style logic internally to direct traffic. Now, for the limitation, and this is important for security architecture. PAC files only cover applications that use and respect the system proxy settings. That's primarily browsers. But think about everything else on a typical laptop. Backup agents, update services, collaboration tools, native email clients, database clients, cloud sync services. Many of these applications make direct internet connections that completely bypass the system proxy. That traffic is invisible to Zscaler when PAC files are your only forwarding mechanism. This is why PAC files are a fallback, not a primary zero-trust solution. They leave significant portions of traffic unprotected, and that's a gap you need to be aware of and communicate clearly when designing or evaluating a deployment. When you're designing site-to-Zscaler connectivity for a branch office or data center, you need to choose between GRE and IPsec. This decision comes down to 4 questions, and I want to walk you through each one clearly because this is a direct exam topic. The first and most important question is, do I trust the underlying network path? If traffic travels over a private MPLS circuit or a dedicated lease line where your carrier provides physical security guarantees, the path can generally be considered trusted. In that case, GRE is typically sufficient. You don't need to encrypt a path that's already physically secure. But if traffic travels over a standard business internet connection, a cable broadband link, a cellular connection, or any public shared infrastructure, that path is untrusted. An attacker could theoretically intercept traffic in transit. IPsec's ESP encryption makes intercepted traffic unreadable, which is exactly what you need in this scenario. The second question is, does my compliance framework require encryption for WAN traffic? PCI DSS, HIPAA, certain government frameworks, they often explicitly require that data in transit be encrypted using strong cryptography. GRE alone doesn't satisfy this. IPsec does. Even if your network path is private, if your compliance requirements say encrypt, the answer is IPsec. The third question is about bandwidth and performance. GRE has minimal overhead. about 24 bytes per packet. IPsec adds more. The ESP header, initialization vector, and authentication data can add 50 to 80 bytes per packet, plus the CPU cost of encryption and decryption. On most branch connections, this overhead is completely negligible. On very high bandwidth data center links, 10 gigabits per second or more, GRE's lower overhead starts to matter, especially on older hardware without AES-NI acceleration. The fourth question is about operational complexity. GRE is simple to configure and troubleshoot. IPsec requires you to correctly align Phase 1 and Phase 2 parameters between your device and Zscaler. Encryption algorithms, integrity algorithms, Diffie-Hellman groups, key lifetimes. Mismatched parameters are the most common cause of IPsec connection failures, and diagnosing them can take significant time. Modern SD-WAN platforms reduce this complexity substantially by automating the configuration and managing rekey events transparently. Regardless of which tunnel type you choose, the high availability design is the same. Deploy at least 2 tunnels per location, each pointing to a different Zscaler service edge. For GRE, use routing metrics or SD-WAN path policies to control primary and backup. For IPsec, configure dead peer detection with appropriate intervals. Probing every 10 seconds with 3 retries gives you roughly 30 seconds to detect a failure and initiate failover. Make absolutely sure your failover path doesn't accidentally route traffic directly to the internet rather than through the backup Zscaler tunnel. A routing mistake like that turns a resilience event into a security bypass. High availability for Zscaler tunnels is not just a reliability requirement. It is a security requirement. Let me explain why that framing matters. If your tunnels fail and you have no backup, one of 2 things happens. Either users lose internet access completely, which causes immediate pressure to bypass Zscaler and get things working again. Or if your routing isn't carefully designed, traffic automatically fails over to a direct internet path. Traffic that should be inspected by Zscaler goes straight to the internet, completely unprotected. That second scenario is called failing open, and it's one of the most dangerous failure modes in any security architecture. The rule is simple. Always deploy at least 2 tunnels per location, pointing to different Zscaler service edges, and where possible, over diverse upstream internet connections. Different service edges means a single service edge issue doesn't take both tunnels down at once. Different upstream connections means a single ISP outage doesn't eliminate all your paths to Zscaler. For GRE high availability, the typical design is 2 GRE tunnels from your branch router or firewall, 1 to service edge A, 1 to service edge B. You then use routing metrics or SD-WAN traffic steering policy to designate one as primary and the other as backup. GRE keep alive probes run continuously on both tunnels. When the primary tunnel stops responding to keep alives, the routing protocol detects the failure and shifts traffic to the secondary. Tune your keep alive interval based on how quickly you need to detect failures. Shorter intervals catch failures faster, but generate more control plane traffic. For IPsec high availability, the mechanism is dead peer detection. DPD sends periodic IKE probe messages to the remote peer. If the peer stops responding after your configure number of retries, it's marked dead and the security associations are cleared. At that point, your device should automatically attempt to establish a new IPsec session with the backup peer. The math here is simple. DPD interval multiplied by retry count equals your detection window. 10 seconds times 3 retries equals 30 seconds. 5 seconds times 2 retries equals 10 seconds. Choose based on your recovery time objectives. For Client Connector and zTunnel 2.0, resilience is built into the software. The DDLS to TLS fallback happens automatically when UDP is unavailable. When the user's network changes, Client Connector detects the event from the operating system, refreshes its configuration, and reestablishes the tunnel, all without user action. Client Connector also periodically polls for policy updates from Zscaler, so any changes you make in the admin portal propagate automatically to all connected clients. On the ZPA side, App connectors in a connector group provide resilience through automatic rebalancing. If one connector fails, ZPA redirects traffic through another healthy connector in the group. Users experience a brief pause, but no manual intervention is required. Monitoring ties all of this together. Resilience mechanisms that operate silently are valuable, but you also need to know when they trigger. If your primary tunnel fails and traffic silently shifts to the backup, you're now running with no redundancy. If the backup also fails before you've restored the primary, you have an outage. Use Zscaler's Tunnel Insights dashboard to monitor tunnel status, throughput, and latency. Configure alerts for tunnel state changes. On your edge devices, enable SNMP traps or syslog alerts. For client connector issues, use ZCC logs and ZDX diagnostics to determine whether problems originate at the endpoint, in the tunnel, or at the service edge. DNS and routing problems are, in my experience, the hardest class of Zscaler connectivity issues to diagnose. And the reason they're hard is that they fail silently. When a GRE tunnel goes down, users lose internet access immediately and alerts fire. When DNS is misconfigured or routing has an unintended bypass, traffic appears to flow normally from the user's perspective, but Zscaler isn't inspecting any of it. Your security controls look like they're working. Your dashboards show green. But you have a gap, and you might not know about it for days or weeks. Let's start with DNS and how it affects ZIA. For ZIA to work, your users need to be able to resolve Zscaler service edge host names. Client Connector resolves these host names to find which service edge to tunnel to. Pack files fetch the pack file URL, which also requires DNS resolution. If your internal DNS server blocks external hostname resolution, which some organizations configure for security, or if a firewall rule drops DNS queries for Zscaler's domains, Client Connector can't find a service edge and nothing works. Make sure every network segment, including remote access, guest Wi-Fi, and cloud environments, can resolve Zscaler's hostnames. For ZPA, DNS plays a more complex and critical role. Application segments in ZPA are defined by FQDNs, fully qualified domain names, not by IP addresses. When a user tries to access an internal application, Client Connector intercepts the DNS query and returns a synthetic IP address in a special range. The user's application connects to that synthetic IP, which routes through ZPA to the App Connector. The App Connector then makes its own DNS lookup, using its own configured DNS server to find the real IP of the internal application server. This is where alignment becomes critical. The App Connector's DNS server must be able to resolve your internal application FQDNs and return the correct internal IP addresses. If the App Connector is configured to use a public DNS resolver like 8.8.8.8, it won't be able to resolve your internal application names, and every ZPA connection will fail. In environments using split horizon DNS, where internal and external DNS zones return different record for the same domain, you need to make sure the App Connector is using the internal DNS zone. A quick lookup from the App Connector's network will confirm whether resolution is working correctly. On the routing side, the core requirement is that traffic follows its intended path, and only its intended path. The most common routing problem is a misconfigured default route. At a branch with a GRE tunnel, the intent is that all internet traffic goes through the tunnel to Zscaler. The branch router needs a default route pointing to the GRE tunnel interface. If someone accidentally adds a more specific route that points directly to the ISP for a particular destination, the traffic bypasses Zscaler. You have no log of it, no inspection of it, no policy applied to it. Overlapping subnets create another class of problems. If your corporate IP address ranges overlap with Zscaler connector addresses or with cloud provider address spaces, routing becomes ambiguous and you get intermittent failures that are extremely difficult to trace. Asymmetric routing, where the outbound and inbound paths are different, breaks stateful inspection and causes drop sessions. Here is the most important practical advice I can give you. Validate every deployment explicitly. After you deploy or change any Zscaler connectivity configuration, do three things. First, Check the Zscaler admin portal and confirm that logs are being generated for users in the affected location. No logs means traffic isn't reaching Zscaler. Second, from a device on the branch network, run a DNS resolution test against a Zscaler Service Edge hostname and confirm it returns a valid address. From an app connector, resolve an internal application FQDN and confirm it returns the correct private IP. Third, run a traceroute from a branch device to an internet destination. The path should show the Zscaler Service Edge in the middle. If the traceroute goes directly from the branch to the ISP without touching Zscaler, you have a routing bypass. Fix it before moving on. Zscaler operates one of the largest security clouds in the world, with service edges deployed in hundreds of locations globally. Major cities, major cloud provider regions, and internet exchange points where traffic naturally concentrates. The goal is that wherever a user is, there's a Zscaler Service Edge nearby, and traffic reaches that nearby edge rather than traveling across the world to a distant one. But getting traffic to the right service edge isn't magic. It relies on specific mechanisms that are worth understanding. The foundational technology is Anycast routing. Anycast means that multiple Zscaler service edges all advertise the same IP address prefix via BGP. When your traffic is sent toward that IP address, the Internet's routing infrastructure delivers it to the topologically nearest node advertising that prefix, not to a fixed single server. You've already experienced Anycast if you've ever used Google's public DNS at 8.8.8.8. That address is served from hundreds of locations worldwide, and your queries automatically go to the nearest one. Zscaler uses the same principle. For pack file deployments, georouting works at the pack file delivery level. When a browser requests the Zscaler pack file, Zscaler examines the public IP of the request, determines the geographic location, and serves back a pack file that contains the IP addresses of the near service edges. The browser then routes its traffic to those specific addresses. Every time the pack file is refreshed, the geolocation check runs again. So a user who travels to a different city automatically gets a pack file pointing to service edges in their new location. For client connector deployments, the process is more active. Client connector resolves Zscaler Service Edge host names through DNS, using Anycast to naturally get directed toward nearby service edges. It may also run latency probes to candidate service edges and select the one with the lowest measured latency, because geographic proximity and network latency don't always match. If a closer service edge is congested or experiencing issues, a slightly farther one with better network path might actually be faster for a specific user. As an administrator, you don't manually assign service edges to users. The platform handles this automatically. Your role is to design the conditions that allow this automation to work well. And the single most important design choice you make here is local internet breakout. Local breakout means that internet-bound traffic exits to the internet directly from the branch or office, rather than being backhauled over a WAN link to a central site first. Without local breakout, a branch in Sydney might send internet traffic over an MPLS circuit to a hub in Singapore, which then sends it to the internet, which routes it to a Zscaler service edge near Singapore. The user in Sydney effectively connects to Zscaler from Singapore, adding hundreds of milliseconds of latency to every single request, every web page, every SaaS interaction. With local breakout, the Sydney branch sends internet traffic directly out the local connection. It reaches a Zscaler service edge near Sydney in 10 to 20 milliseconds. Every application runs faster. Users notice the difference immediately. This is especially critical for latency-sensitive workloads like Microsoft Teams, Zoom, Google Meet, and any real-time collaboration tool. Your BGP configuration and WAN routing design also affect geo-routing quality. Make sure your route advertisements accurately reflect where your traffic originates, and avoid asymmetric routing designs that could cause your traffic to exit from a different location than expected. Finally, use Zscaler's diagnostic tools to validate geo-routing after deployment. In the ZIA portal and through ZDX, you can see which service edge each location or user is connecting through. If a branch in Sydney shows up as connecting to Singapore, that's your signal that local breakout isn't configured or that routing is sending traffic in the wrong direction. We've covered a lot of ground in this module, so let me close with the 6 things that you absolutely need to have internalized before your ZDTA exam and before you go and design or troubleshoot a real Zscaler deployment. The first takeaway is that zero trust means identity over network. Network location no longer determines trust. Every time the pack file is refreshed, the geolocation check runs again. So a user who travels to a different city automatically gets a pack file pointing to service edges in their new location. For client connector deployments, the process is more active. Client connector resolves Zscaler service edge host names through DNS, using Anycast to naturally get directed toward nearby service edges. It may also run latency probes to candidate service edges and select the one with the lowest measured latency, because geographic proximity and network latency don't always match. If a closer service edge is congested or experiencing issues, a slightly farther one with better network path might actually be faster for a specific user. As an administrator, you don't manually assign service edges to users. The platform handles this automatically. Your role is to design the conditions that allow this automation to work well. And the single most important design choice you make here is local internet breakout. Local breakout means that internet-bound traffic exits to the internet directly from the branch or office, rather than being backhauled over a WAN link to a central site first. Without local breakout, a branch in Sydney might send internet traffic over an MPLS circuit to a hub in Singapore, which then sends it to the internet, which routes it to a Zscaler service edge near Singapore. The user in Sydney effectively connects to Zscaler from Singapore, adding hundreds of milliseconds of latency to every single request, every web page, every SaaS interaction. With local breakout, the Sydney branch sends internet traffic directly out the local connection. It reaches a Zscaler service edge near Sydney in 10 to 20 milliseconds. Every application runs faster. Users notice the difference immediately. This is especially critical for latency-sensitive workloads like Microsoft Teams, Zoom, Google Meet, and any real-time collaboration tool. Your BGP configuration and WAN routing design also affect georouting quality. Make sure your route advertisements accurately reflect where your traffic originates, and avoid asymmetric routing designs that could cause your traffic to exit from a different location than expected. Finally, use Zscaler's diagnostic tools to validate geo-routing after deployment. In the ZIA portal and through ZDX, you can see which service edge each location or user is connecting through. If a branch in Sydney shows up as connecting to Singapore, that's your signal that local breakout isn't configured or that routing is sending traffic in the wrong direction. That we've covered a lot of ground in this module. So let me close with the 6 things that you absolutely need to have internalized before your ZDTA exam and before you go and design or troubleshoot a real Zscaler deployment. The first takeaway is that zero trust means identity over network. Network location no longer determines trust. It doesn't matter if the user is in the office, at home, or on the other side of the world. What matters is who they are, their authenticated identity, and the state of their device, whether it meets your posture requirements. Every Zscaler policy decision starts from that foundation. The second takeaway is that the forwarding method must match the use case. Client connector with zTunnel 2.0 is for user devices, laptops, phones, desktops. GRE and IPsec tunnels are for fixed sites, branches, headquarters, data centers. Cloud connectors are for cloud workloads. Pack files are the fallback for browser-only, agent-not feasible scenarios. Using the wrong component doesn't just limit capability. It creates security gaps where portions of your traffic bypass Zscaler completely. The third takeaway is the relationship between zTunnel 2.0 and ZIA Cloud Firewall. This is a hard architectural requirement. zTunnel 2.0 is required for Cloud Firewall. Legacy tunnel modes and pack files are proxy-based. They handle HTTP and HTTPS only. zTunnel 2.0 encapsulates at the IP layer, covering every protocol and every port. That full protocol coverage is what makes Layer 7 firewall inspection possible. If any exam question mentions ZIA Cloud Firewall, the answer involves Client Connector with zTunnel 2.0. The fourth takeaway is the GRE versus IPsec decision framework. Start with trust. Untrusted public internet path means IPsec. Trusted private one means GRE may be sufficient. Then check compliance. If your framework mandates encryption, use IPsec regardless of the network trust level. For very high bandwidth data center links on trusted paths, GRE's lower overhead is an advantage. And regardless of which you choose, always deploy at least 2 tunnels per location to different service edges, with proper keep-alooves or dead peer detection for rapid failover. The fifth takeaway is that DNS and routing are the silent killers. A misconfigured DNS zone breaks ZPA access to specific applications in ways that are very hard to trace. There's no obvious error message. Things just don't connect. A misconfigured default route creates a traffic bypass where users can access the internet, but Zscaler isn't inspecting anything. Validate every deployment explicitly. Check that Zscaler logs are being generated, test DNS resolution from every network segment, and run trace routes to confirm traffic is traversing Zscaler. The sixth and final takeaway is that geolocation and service edge selection are automatic, but your network design either helps or hurts this automation. Zscaler handles service edge selection through Anycast and DNS-based measurement. You don't manually assign edges to users. But local internet breakout at branches is your responsibility, and without it, traffic backhauling to a central site defeats the geo-optimization entirely and degrades user experience significantly. That's the module. Review these 6 takeaways, practice applying them to scenario questions, and make sure you can explain the why behind each one, not just recite it. The ZDTA exam is a design and decision-making exam. If you understand why each forwarding method exists and what goes wrong when you pick the wrong one, you're ready for this section. Good luck.